Okay, good day again, everyone. And we are still on our anemia that is associated with increased red cell destruction. But if specifically, we will be discussing the intrinsic hemolytic anemia. So again, I am Eden, and with my group mates, Carmel, Trisha May, Sitaranisa, and Edgemia, we're going to share to you our understanding in the intrinsic hemolytic anemia. And for our coverage in this discussion, of course, the intrinsic hemolytic anemia, which is subdivided into two, the hereditary and acquired, wherein under hereditary, there are membrane disorders, enzyme disorders, hemoglobin disorders, and under acquired intrinsic hemolytic anemia, we have our membrane defect. And for our reference, we refer it to our reference book, Rodax Hematology 6th edition. So again, from our previous video, we introduced to you that this intrinsic hemolytic anemia is all about the defects on the RBC itself. And for this video, we will be going to detail each of its defect. So okay, to start, may I introduce to you Miss Najmia for the hereditary membrane disorders.
Good morning. I'm here to discuss about the membrane disorders, which are hereditary. Let's proceed. Okay, the first one, we have the hereditary spherocytosis. But before that, let me just give you a little introduction about the membrane disorder. So membrane disorder is a disorder of the erythrocyte membrane. So when the RBC membrane disorders are inherited due to the mutation in various membrane or skeletal proteins, result in decrease of red cell deformability, which results in the because of the repeated passage through the capillaries and also the reduced lifespan, which is 120 days, and premature removal of RBC to the circulation. The first one, we have the hereditary spherocytosis. It is an inherited disease that affects the red blood cells caused by abnormal red cell membrane protein composition, which includes spectrin, actin, protein 4.1, and acurin, and protein. I'm going to have to give definition to that later. So it also associated as mild anemia. So for this one, a test for hereditary spherocytosis, the first one is osmotic fragility test, which is the most common. It is the confirming test which reflects the shape of the RBC. The specimen used for this test is the fresh heparinized blood and the defibrinated blood, where the whole blood and fibrin has been removed. The second test is autohemolysis test. This test lies in the differential diagnosis for PK deficiency and G6PD deficiency. So this is the best confirming for the false negative results, and its principle is measure the series of changes, and that could be loss of membrane and becomes more spherocytic in 37 degrees centigrade for 48 hours. And for the last test for this hereditary disorder is the direct antiglobulin test, useful in the differential diagnosis of HS to those immune hemolytic anemias. For this test, it helps detect antibody on the red cell surface. Next. Okay, we have the hereditary eleptocytosis. So when we say elepto, it is an elongated oval-shaped RBCs and commonly caused by three skeletal abnormalities. For this one, we have the abnormal spectrin interaction. So spectrin, just like what I've said, spectrin is it is a cytoskeletal protein that lines the intracellular side of plasma membrane of the cell. And second one, the defective ankyrin protein 3 interaction. So ankyrin, same with the spectrin, it is also a skeletal proteins that links the membrane band of protein to the underlying cytoskeleton. And then the deficiency of protein 4.1, and then increase of greater than 25% non-hypochromic eleptocytes on the blood film, which is normally less than 15%. Next. The third one, we have the hereditary pyopoikilocytosis or HPP. It is a rare hemolytic disorder of defective spectrin function and primarily in Black children. So again, we have here the defective spectrin function. It is the major skeletal protein of RBC membrane. The laboratory findings for this one is the extreme microcytosis, striking micropoikilocytosis, fragmentation, and other bizarre form. It is also, we have the HPP red cells fragments at 45 to 46 degree centigrade, and the normal cells is for 49 degrees centigrade. This one, it is for autosomal recessive disorders of RBC membrane. And for the fourth one, next slide, please. We have the hereditary stomatocytosis, is also known as hydrocytosis overhydrated. I'm going to explain what is called overhydrated. It is a clinically characterized by hemolytic anemia. It is a rare, dominantly inherited disorder of RBCs associated with increased membrane permeability to monovalent cation and increased activity of sodium, potassium ATPase. So when we say monovalent cations, it is permeability is relative to potassium. So it is associated with high potassium and sodium content. So mag-result into an increased membrane of permeability. So what happened here is that the membrane of the cell leaks the sodium and potassium ions. That's why it is overhydrated. And this is also the first type of a rare autosomal dominant congenital anemia. And it is characterized by alteration of RBC hydration. And then the last one is the hereditary serocytosis, also known as dehydrated hereditary stomatocytosis. So it is the opposite of the first one. This is dehydrated. Also, this is the second type of the rare autosomal dominant congenital anemia. They increase the cation permeability of the membrane, which leads to erythrocyte dehydration, a rare red blood cell membrane disorder resulting in hemolytic anemia with diverse presentation and iron overload. Compared to the last one, we have a leaking of potassium and sodium. For this one, we have iron overload, and that is why it is dehydrated. And that is all for these membrane disorders. Let's proceed to the order reporter.
So we are still in the hereditary, which is in the enzyme disorders, hemolytic anemia associated with enzyme disorder. So next. So the first hemolytic anemia associated with enzyme disorder is the glucose 6-phosphate dehydrogenase deficiency, or the G6PD. So RBCs normally produce free oxygen radicals and hydrogen peroxide during metabolism and oxygen transport, but they have multiple mechanisms to detoxify this oxidant. So occasionally, RBCs are subjected to an increased level of oxidants or the oxidant stress as a result of exposure to certain oxidizing drugs, foods, chemicals, and herbal supplements, and even through reactive oxygen molecules produced in the body during infections. If allowed to accumulate these RBCs, this reactive oxygen species would oxidize and denature hemoglobin, membrane proteins, lipids, and ultimately cause premature hemolysis. So therefore, the capacity of RBCs to detoxify oxidants, especially during the oxidant stress, is critical to maintain their normal lifespan. So this G6PD is the most common enzyme-related hemolytic disorder. It is one of the important intracellular enzymes needed to protect hemoglobin and other cellular proteins and lipids from oxidative denaturation. So the deficiency of G6PD limits the reaction of NADPH or the nicotinamide adenine dinucleotide phosphate, which makes the cell vulnerable to oxidative denaturation of HB. So this also the hemolytic episodes become severe during intercurrent illness or exposure to oxidant drugs. Next, please. So the next one is the blood findings in under the G6PD, which is the first one is the characteristic bite cells, which is the irregularly contracted cells, which represents by hence body craters are often seen. And the next one is the hinged bodies, which represents denatured HB stained with supravital stain, the methyl violet into deep purple, but not with Rowanowski stain. So the next blood finding is the G6PD phabism. Phabism is a rare severe hemolytic episode that occur in some G6PD deficient individuals after ingestion of faba beans. So this phabism can initially manifest with a sudden onset of acute intravascular hemolysis within hours of ingestion. Faba beans or hemolysis can occur gradually over a period of 24 to 48 hours, equivalent of 2 days. So this G6PD fabism is the first sign is the hemoglobinuria. This is also the subgroup of G6PD Mediterranean that exhibits several hemolytic anemia within hours after eating these faba beans. So the next one is the laboratory test. Under G6PD, we have 3 tests: the dye reduction test, methemoglobin reduction test, the ascorbic cyanide test, the fluorescent spot test. So the first one is the dye reduction test, which is it uses the same G6PD enzymatic reaction but have a second step in which the NADPH reduces a dye, giving a visual observe of color change. So the principle of this test is to detect NADPH generation by G6PD through the reduction of methemoglobin to hemoglobin with methylene blue as the facilitator. So the next one is the ascorbic cyanide test, or which is produces oxidants causing oxidation of HGB. So the principle of this test is to measure the ability of normal cells to detoxify hydrogen peroxide with incubated with ascorbate. So the last test is the fluorescent spot test, which is the principle of this test is based on the NADPH. NADPH generated in the reaction is fluorescent, while the NADP in the reagent is not fluorescent. So let's move in the second hemolytic anemia associated with enzyme disorder, the pyruvate kinase deficiency. So this pyruvate kinase deficiency or the PK deficiency is a rare K enzyme of the glycolytic pathway of RBCs. So this pyruvate deficiency inhibits glycolysis that results in increase of 2,3-DPG levels. So therefore, anemia is well tolerated. So this PK deficiency also is an autosomal recessive disorder. It is the most common form of hereditary non-spirocytic hemolytic anemia, and it is also found in worldwide. So it leads to marked reduction in adenotriphosphine production, which is necessary for our sodium minus potassium. Next. So let's move to pyruvate kinase laboratory test. The first one is the autohemolysis test, which have three patterns of hemolysis. The first is the type 1, which is the autohemolysis is mildly increased, that is partially corrected by glucose seen in G6PD deficiency, hereditary elliptocytes, and unstable HB disease. The next type is the type 2, which is the autohemolysis is greatly increased, that is not corrected by glucose and associated with pyruvate kinase deficiency. So the third one is the hereditary spirocytosis, which is the autohemolysis is greatly increased but can be corrected by either glucose or the adenotriphosphate. So the next laboratory test is the fluorescent spot test, which is the screening test for pyruvate deficiency. And the third laboratory test is the quantitative assay of pyruvate kinase, which is used to confirm abnormal spot test results. Tapos na. Next na.
Okay, so we are on our third enzyme disorder, still under in our hereditary intrinsic hemolytic anemia, and that is the glycolytic enzyme deficiency. So by the way, what is glycolytic enzyme? So glycolytic enzymes, so these are the enzymes that are important or that plays an important role in the conversion of our glucose into ATPs. And also, these are specifically under Embden-Meyerhof pathway. So these are the enzymes that plays an important role, the 2,3-diphosphoglycerate mutase and 2,3-diphosphoglycerate phosphate deficiency and glutathione synthetase, and also under hexose monophosphate shunt. By the way, this hexose monophosphate shunt, so it is still under the Embden-Meyerhof pathway, where its K-role enzyme are gamma-glutamyl cysteine synthetase and glutathione synthetase. So again, I have a question. So why do you think RBCs are affected when there is glycolytic enzyme deficiency? So okay, so take note that our RBCs are anucleated, meaning they have no nucleus and they have no mitochondria. So meaning that they cannot make their own energy to be functional. So by that, they rely on other sources. So specifically, they rely their energy on Embden-Meyerhof pathway. So if maski isa lang na enzyme is deficient ang Embden-Meyerhof pathway, so therefore it cannot be able to make pyruvate, cannot be able to make ATP. So wala ring ATPs or energy na magsusupport sa ating RBCs. And for that, so it will lead to the destruction of our RBC, or it will not be functionable. And for the next slide, I will be going to detail that one. So just take note that in 2,3-DPG mutase, so it is responsible for the catalytic synthesis of 2,3-BPG from 1,3-biphosphoglycerate. So take note that it is the 2,3-DPG mutase that is responsible for the conversion of 1,3-biphosphodiesterate into 2,3-biphosphodiesterate. So remember that in the oxygen affinity, so that this 2,3-biphosphodiesterate plays also an important role, for it acts as an allosteric um, molecule. No? If you still remember pa, na it binds at the hemoglobin molecule and it stabilizes the T state of hemoglobin. So once na ma-stabilize na ang T state sa hemoglobin, so it lowers the affinity of hemoglobin for oxygen. And take note, so ito yon, saan ba yung wait? The 2,3 biphospho, so it is around here. So again, so it also, this is the 2,3-BPG that will act as a allosteric molecule to be able to increase or decrease the bind of the hemoglobin for oxygen. So if, of course, if wala ang 2,3-diphosphoglycerate mutase, then wala ring mag-convert ng 1,3-BPG into 2,3-BPG. So that is also important if we have a normal value of this 2,3-DPG mutase. And next, we have the 2,3-DPG phosphate. And this 2,3-DPG phosphate is responsible for the modulation of our oxygen dissociation curve. So take note that if there are increased 2,3-DPG phosphate, so it will be shift to the right in our oxygen dissociation curve. So there is shifting to the right. So take note that the shifting of the curve to the right, so it indicates that there is a decreased affinity of the hemoglobin for oxygen. So remember that if there is decreased affinity of the hemoglobin for oxygen, so there is also increased tendency to give up oxygen to the tissues. While in decreased 2,3-diphosphoglycerate phosphate, so therefore also opposite to the increase, it will shift to the left, and it indicates that the affinity and so an increased tendency for hemoglobin, that is to take up and retain oxygen. So that is the differences of the two, shift to the right and shift to the left. And also for the hexose monophosphate shunt, so as I said a while ago, that this hexomonophosphate shunt is still part in our Embden-Meyerhof pathway. So it is from our glucose and phosphoglycerol phosphate down there. And under this hexose monophosphate shunt, so take note that it is responsible for the production of energy, RNA and DNA. And also, its K role is to reduce oxidative radicals. So, diba, we are always exposed on oxidative radicals. And these oxidative radicals, though they tend to destroy microorganisms, but they have also downside. And they also destroy tissues, and one of its major downside is that it damages our cell membrane of the RBC. And also in this shunt pathway, we have our K enzymes, and that's are the glutathione synthetase and the gamma glutamyl cysteine synthetase. So the glutathione synthetase, it is responsible for the metabolism of our glutathione, and this gamma glutamyl cysteine, it is responsible for catalyzing the first and rate limiting step in the synthesis of glutathione. So take note that this two enzyme is responsible for the metabolism to create glutathione. So now what is the role of the glutathione and why it is needed to be formed? So of course, in order to be this glutathione to be functional, first we have to or it must be reduced by the NADPH. So once it will reduce into so once this glutathione is reduced by the NADPH, so this glutathione can be able to convert our oxidative radicals into water and oxygen. So meaning, hindi na makaharm ang oxidative radicals sa red blood cells once ma-reduce ang glutathione. Because these oxidative radicals will be converted into water and oxygen by the reduced glutathione. So that is why importante yung enzyme na ito under HMP shunt pathway, because it creates glutathione, and in order for the glutathione to be reduced, it should be act upon by the NADPH. So once it is reduced, so the harmful oxidative radicals that can be able to destroy our RBC will be converted into oxygen and water. So that is the mechanism here. So I hope you all understand that. And now we are our fourth and last enzyme disorder, still under our hereditary intrinsic hemolytic anemia. And it is the pyrimidine 5' nucleotidase or PN deficiency in this enzyme. So there is accumulation of pyrimidines, meaning mapile up ang ating RNA. So once mapile up ang ating RNA, so since they are deficient and they cannot be able to degrade RNA, they cannot be able to so it will result to basophils. Now, aside from that result, we have also the splenomegaly, so of our spleen. So though, according to the reference book, though the person with splenomegaly will undergo splenectomy or removal of spleen, so maski na naka-undergo sila doon, though they have no notable improvement pa rin. So that is the danger of this enzyme disorders. So again, I hope you understand that. And we are done on our enzyme disorders. And for our hemoglobin disorders, may I introduce to you Ms. Carmel?
So hi everyone. Again, I am going to be discussing the hemoglobin disorders, but first let us know what is a hemoglobin disorder. So a hemoglobin disorder, we can also call it a hemoglobinopathies, which are rare blood conditions that are caused by problems with hemoglobin. So hemoglobin is a protein in the blood that carries oxygen, and we all know that oxygen is a very important na kuan sa to ang body. Kaya in order for us to move or do the things that we want to do, we need oxygen and nutrients in our body. And because of hemoglobinopathies, we are unable to do those things. So next, we have here the sickle cell anemia. So now let's have the sickle cell anemia, or we can also call it a sickle cell disease. So it is a severe chronic hemolytic anemia of early childhood. So when we say sickle cell anemia, it is inherited red blood cell disorder in which there aren't enough healthy red blood cells to carry oxygen throughout your body. So normally, the flexible round red blood cells move easily through blood vessels. But in sickle cell anemia, the red blood cells are shaped like sickles or crescent moons. So these rigid sticky cells can get stuck in small blood vessels, which can slow or block blood flow and oxygen to parts of the body. So we have here sickling cells due to decrease in oxygen tension, the hemoglobin S that polymerizes, forming rigid tacloids, or which we call fluid crystals. So the complications here, we have the hand-foot syndrome or sickle cell dactylitis. We have the sequestration crisis, the functional asplenia, autosplenectomy, the vaso-occlusive crisis, aplastic crisis, and hemolytic crisis. So signs and symptoms of sickle cell anemia usually appear around 5 months of age. So they vary from person to person and change over time. So signs and symptoms can include, we have here the anemia, which is sickle cells break apart easily and die, leaving you with too few red blood cells. So red blood cells usually live for about 120 days before they need to be replaced, but in sickle cells, usually they die in 10 to 20 days, leaving a shortage of red blood cells anemia. So without enough red blood cells, so your body can't get enough oxygen, causing fatigue. So we have here the episodes of pain, which periodic episodes of pain called pain crisis are a major symptom of sickle cell anemia. So pain develops when sickle cell-shaped red blood cells block blood flow through tiny blood vessels to your chest, abdomen, and joints. Pain can also occur in your bones. So here we have the so the hematuria and hypostenuria in adults. This is due to the inability of kidneys to concentrate urine. So confers protection in children against malarial, which has this organism, the Plasmodium falciparum infection. Then we have the laboratory test. We have the sickling test. We have the sickling test, the solubility test, which uses dithionite, and the hemoglobin electrophoresis, which is cellulose acetate at a pH of 8.6. So when we said 8.6 Gani, it is alkaline. And also the hemoglobin electrophoresis, it's normal, it's HbA, we have 50 to 65%, and for HbS, we have 35 to 45%, and for the HbF, which is normal, the HbA2, which is normal, or up to 4.5%. So we have to know that, or we have to put it in mind that when we have a less than 35% of HbS, and microcytosis is usually are associated with coexistence of one or more alpha thalassemia genes. So I am going to discuss later the thalassemia. Next slide, please. So now let's have the hemoglobin C3, or the HbAc, which is the heterozygous state, is asymptomatic or without anemia. So the HbC, it is a variant hemoglobin with a mutation in the beta-globin gene, causing substitution of glutamic acid for lysine at position 6 of the globin chain. So another amino acid substitution occurs at the same site of beta-globin, causing the sickle cell hemoglobin, and the HbC may be present in the heterozygous state, as what I have stated there. So the homozygous state and a variety of compound heterozygous states, such as the hemoglobin C, beta thalassemia, sickle cell hemoglobin C disease, which leads to a sickling disorder generally less severe than sickle cell anemia. Mild hypochromia and target cells, which are up to 40%, may only be present. And also, we have here the hemoglobin electrophoresis, which we have HbA, which is 50 to 60%. For HbC, we have 30 to 40%. HbF and HbA2, which are normal. And we have to take note that less than 30% of HBC and microcytosis usually are associated with the coexistence of alpha thalassemia. Now let's have the unstable hemoglobin. So hemoglobin that are variants having unstable hemoglobins that precipitate with the red cells as Heinz bodies. So Heinz bodies is our congenital Heinz body hemolytic anemia, which in turn damage and shorten red cell survival. So hence, they are readily removed by the splenic macrophages and other RES. So Heinz bodies, no, these are pale blue, and HBH inclusions, we have greenish blue, which are both stained with brilliant crystal blue. So next. So now let's move on to the beta thalassemia. So beta thalassemia, which refers to an impaired production of beta chains. So therefore, HbF or the HbA2 is often increased with respect to HbA. So these are the major mga types of thalassemia. We have thalassemia major or called anemia hemolytic. So this characterized by increased gamma chain production, which increased HbF and excess alpha chains form precipitate in normoblast or RBC, causing an early destruction that results to ineffective erythropoiesis and severe hemolytic anemia. So clinical findings may include prominent frontal bones, cheekbones, and jaws, in part mongoloid. Then the blood findings, so severe microcytic and hyperchromic anemia. We have extreme poikilocytosis with bizarre shapes. We have the NRBCs are markedly increased, hence an increased RBC count. And also we have marrow storage, iron, and sideroblasts are increased. So the electrophoresis for these is we have HbA, which are occasional or absent, HbF elevated up to 98%, and for HbA2 we have 2 to 5%. Now we have the thalassemia intermedia. Growth and development in children is relatively normal. Clinical findings are less severe than the thalassemia major. So blood findings, we have moderate anemia, increased RBC count, depressed MCV and MCH. We have also the HB electrophoresis. For HbF, we have normal to elevated, and for HbA2, we have variable, and HbA, we have usually absent. No, then we have here the third one, thalassemia minor or the Colles trait, which means there is no anemia, you are just a carrier. So rarely produce significant physical findings or symptoms. And also we have the blood findings. There is usually no anemia because you are just a carrier. So elevated RBC count, but reduced HB and HCP. We have low MCH, which is less than 22 pg, and MCV, which is 50 to 70. And also we have low to normal MCHC, elevated marrow storage iron. And now let's go to the thalassemia minima, which is the silent, which also known as the silent beta thalassemia trait. So it is mostly no symptoms. Okay, from the word itself, it is silent. So there are no symptoms or abnormal physical sign. So for the blood findings, it has a normal red cell morphology and count. The MCV and MCH are within normal or slightly depressed, and we have normal hemoglobin electrophoresis. So now let's move on to the alpha thalassemia. So alpha thalassemia, which refers to a decreased production of alpha chains. Therefore, all three hemoglobins, which are the HbA, HbA2, and HbF, are decreased proportionally. So we have here the major forms. We have the hydrops fetalis, the HbH disease, this thalassemia minor, and silent carrier. So first, let's have the hydrops fetalis. So hydrops fetalis, this is a serious condition. No? It occurs when abnormal amounts of fluid build up in two or more body areas of a fetus, so or newborn. So it is a symptom of underlying problem. So hydrops fetalis, from the word itself fetal, it happens on on the fetus. No, napa siya sa tummy sa iyahang mommy. Now let's have here the hemoglobin H disease, which is a severe anemia develops due to reduced formation of alpha globin chains. So in this condition, as in other forms of thalassemia, there is an imbalance of globin chains needed to form hemoglobin. And for this thalassemia minor, uh, there are two missing or mutated genes na naaderi. And also, having alpha thalassemia trait, children with this condition may have red blood cells that are smaller than normal. So we call it the microcytosis, and sometimes very slight anemia. Next, we have here the silent carrier, the last one. So blood tests are usually normal. Your red blood cells may be smaller. So from the word itself, silent, no, it does not show any symptoms. So red blood cells may be smaller than normal. Being a silent carrier means you don't have signs of the disease, but you can pass the damaged gene onto your child. So when you say silent carriers, no, you are only a carrier. So you do not, dili ka makaagi og symptoms or mga signs that you have the alpha thalassemia. But you can pass it to, kanang example, mga naka or something like that. So, next.
Now for the acquired intrinsic hemolytic anemia that is associated with membrane defects. So may I introduce to you Mr. Shimei Montejo for this discussion about membrane defect.
So, membrane defect in paroxysmal nocturnal hemoglobinuria or PNH. It is an acquired intrinsic hemolytic red cell defect that shows an abnormal sensitivity to a complement at low pH, which results in complement-mediated release. And it is also characterized by chronic intravascular hemolysis with or without obvious hemoglobinuria. It is typical sleep-related hemoglobinuria. It passage of red to brown urine upon rising, which chiefly occurs at night when blood pH falls. Next, then. So this will be the blood findings. So pancytopenia is common. This pancytopenia is common with neutropenia and thrombocytopenia. So pancytopenia is when a person has a decrease in all three blood all types. And neutropenia is when a person has a low level of neutrophils, and thrombocytopenia is when your blood platelet count is low. So this will be this three as described as decrease of um, decrease has a level of low of blood kanang ubos ilang kuan tanan bitaw mo ano siya ang gakuan kanang kuan nga ubos tanan. So Next is red cell acetylcholinesterase and neutrophil alkaline phosphatase are usually decreased. So, mao to siya kani pod uh, decrease pod. So also thrombotic complications are common. So ang thrombotic day kay kuan kana when uh, thrombotic means the formation of a blood clot. So naa siya complications. So um dire kuan nga kana ma-find out kung kuan ba kanang ay dire ma-find out nga naa jay kuan kanang um, complications. So next. So there will be a laboratory test for paroxysmal nocturnal hemoglobinuria or PNH. So sucrose, number one is sucrose hemolysis test. So sucrose or sugar water hemolysis test is a blood test to detect fragile red blood cells. It helps by testing how they will withstand swelling in a sugar or sucrose solution. So the result is in in PNH, a proportion of red cells mao to siya kanang red cells is abnormally sensitive to the complement mediatases. So next. So number two, acidified serum test or HAMS test. So it is establishes the diagnosis of PNH or and demonstrating a characteristic of abnormalities in PNH. In the red blood cells by signified. So kani siya kay in result the PNH usually 10 to 50% of the cells are are lice. Lice. So next. So number three, flow of cytometry. It is a laboratory test that specific and relatively simple and accurate. So next. Mana naman.
Okay, and that will be all for the intrinsic hemolytic anemia. So under hereditary, we have membrane disorders, enzyme disorders, and hemoglobin disorders. And for acquired hemolytic anemia, we have membrane defect. So discussion, and we will be seeing you in the next video, specifically in the classification of hemolytic anemia under the spectrum of extrinsic hemolytic anemia. So see you on another video.